So direction family means all the directions you have, the spacing of atoms along, no matter which direction, they're all the same. They're all equivalent. And if we have family of directions, we use the notation that is the angled bracket. So for example, family of direction 1, 0, 0. So this is a family of directions. Can include all the directions that share the same spacing of atoms. In this case, if we look at a unit cell, so all the directions along the axis are the same, belongs to the same direction family. So we can have pointing that way along the x-axis, or you can go other way around. You can also do this. Start from that corner, goes to the front corner of that unit cell. Doesn't matter which way you go. They're all equivalent. So let's write out how many family members does this 11100 has. So we could have, okay, here I'm writing directions. So this is a square bracket. 100, 010. This is a test for your possibility statistics. How many different combinations we have? 001. Are we done? Do we have more family members for family 100? Yes. So you can change the orders of 0 and 1s as long as you have 2 zeros, 1, 1, 1, you're good. And also you can switch the negative signs. You can add negative signs to any of them. Then you have a lot of combinations. So they all belong to this 100 family. And this is only for the cubic system, cubic crystal system. Okay, so that's a family of directions. All right, now let's talk about planes. We're going to do the same thing, tell you the steps, how to find the indices for crystallographic plane. Then we're going to talk about plane family. It's kind of like direction family. We have a plane family, we use curly bracket, and very similar. Okay, now let's look at planes. Planes are a little bit tricky. So same deal, plane, crystallographic plane has 3 numbers. That's for most of the cases. So we call it Mueller indices. Use H, K, L. That represents the symbols for the Mueller indices for plane. And for plane, any two planes that are, if they're parallel to each other and they're equivalent, they can share the same indices. Okay, and share same indices. Okay. Now let's look at the steps. How to find out the plane indices. Let's draw a unit cell. Z, Y, and X. Okay. Let me use a blue color to draw the plane we want to find the crystallographic indices. So that plane cut kind of halfway from that outside edge and pass through the origin. Oh, this is a really bad angle. But can you see that? That's the plane that cut through that unit cell. Let me redraw this. Okay, so I redraw the whole thing in this angle. That it looks more clear. So that's a plane cut through the unit cell. How to find out the crystallographic plane indices HKL for this plane? So there are 4 steps. Step 1 is to look at your unit cell and the coordinate system to determine if the given plane cross through the origin. Okay, now let's look at this unit cell and this plane. Is the plane passed through the origin? Yes or no? Yes, right? That plane crossed through that origin. So if that is passed through the origin, if yes, then we need to construct a new coordinate system. If no, the answer is no, we step 2, step 2. If yes, let's create a new origin, then jump to step 2. Okay, how to create a new origin? So the new origin you created for this should make sure that plane doesn't cross through that origin. So either let's just make it consistent. If you see a problem like this, that's all great. Let's make a new origin. Use another corner of that unit cell as a new origin. I will pick this point as a new origin and build my X, Y, and Z. In this case, this is my new Z. It's OZ, X, and Y. My new X direction, the Y it's the same. So that's my new origin. So when you look at the new origin and, okay, good. The plane doesn't cross through the origin anymore. So we're good. Now we can move on to step 2. In step 2, we want to find out the interceptions of the plane with each axis. We have 3 axes, which means we're going to have 3 interceptions. Uh-oh. Okay, so let's first look at x-axis. Let's use capital letter A for the intersection. For the intersections. Okay, let's go back here. What is the intersection between that plane and our new x-axis? All right, let's don't confuse this. Let's read the old ones. Okay. What is the intersection between that green x direction and our plane? Do we have an intersection? No. If we don't have an intersection and the intersection is infinite, you just write infinite there. So A, in this case, is infinite because we don't have any interceptions. Parallel. That's when you have the planes parallel to the axis. Now let's look at y-axis. Let's use B for the interception. Okay, let's look at y. What is the interception of that plane with y-axis? Y is going that way. The plane goes backward. Cut at, what's the length there? So that from that point all the way towards the interception, that's one edge length of that unit cell on the y direction. So it is negative b, right? We use b for the edge length for y direction. So the interception is negative b. Okay, now let's look at z. What is interception on z-axis? Z is vertical and that plane, and Z has an interception, which is, should give you, yeah, I forgot to mention that that point is half the length of that Z direction. So it's half, 1/2 C. So here is 1/2 C over there. So for C, it's 1/2 C, small c. Now we have the interceptions with each axis, A, B, and C. We can jump to step 3. Okay, in step 3, we want to take the recepcons of A, B, and C and to find out what is H, K, and L. So here's the equation for H, K, and L. H The first index equals a, small a, which is the edge length of the unit cell on x direction, divided by a. So take the a, recepcon of a. So a is the edge length. A, the capitalized A, is the one we found in step 2. In this case, it's infinite. Let's plug in the value, infinite. What's the result of A divided by infinite? 0, right? If you divide by something by infinitely large, the result is going to be 0. Okay, let's look at K. K is equals small b divided by capital B. In this case, we have b divided by negative b. We have negative 1. Let's look at L. L equals small c divided by capital C. We have c divided by 1/2 c. We got 2. Okay, very good here. Now we find HL, HKL, all 3 numbers. What's the notation for plane, crystallographic plane again? Do we use bracket, parentheses, or angle bracket? Step 4, parentheses. Put HKNL inside of a parenthesis. Parentheses 0. If you have negative, that we have negative 1 over there, you use the overhead bar. So we have 0, 1 bar, and 2. That's a crystallographic plane we're looking at here. So as step 4, I want you to check a few things. Check if there is any fraction number. What happens if you have a fraction number? So in crystallographic plane indices, we don't have fraction number. So you want to time all 3 numbers with the minimum common, what's that called? Common number, to make sure everybody is integer. We don't want to have no fraction numbers. That's first thing. And another thing is to check signs. Make sure you don't have something like this. 0, 1, 2. That's not right. Put overhead bar for negative sign. Okay. So those are the 4 steps to find crystallographic planes. The most important step is that step 1. You have to make sure your plane doesn't cross through the origin. If it does, create a new origin. All right, then step 2, find the interceptions. Step 3, plugging them into the equation to find HKL. Step 4, just put them in the parentheses. You get the crystallographic plane indices. All right, any questions? Okay, now, can we do other way around? Wait, let me think. Okay, let's do this. Now let's do a practice. Let me draw a plane. You're gonna tell me what's the indices. Follow the 4 steps. Okay, let me use a red color. So this plane is cut through the, start from the one corner of that cube all the way to the bottom diagonal, the face diagonal. So that's the plane you are looking at. Okay, your job is to follow steps to find out what is the plane indices for this plane. So step one, you need to determine if this plane passed through the origin. Now the good news is, no, this plane does not cross the origin. So we're good. We can just use the given origin. You can jump to step two, right? Step two, find all the interceptions. Interception with X, it's positive A. Interception with Y, positive Y. Good thing is they're all at the corner of the cube. Interception with Z, it's just Z, the C. And plug them into the equation. 1, 2. Okay, who can tell me what's your answer for this? What's H, K, and L? What's your number for H? 2, 1, 1, or 1, 1, 1. Put them into parentheses in step 4. 1, 1, 1. That's the crystallographic plane indices for this highlighted plane. Okay, plane 1, 1, 1. Let's write it down. It's very important for specific crystal structure. It's important for, so for metals, we learn 3 different crystal structure: FCC, BCC, and HCP. So this direction, 1, 1, 1, it's very important for FCC. Why is that? Think about, look at, just imagine where are the atoms instead of unit cell for FCC? You can put there here. Let me use a different color. If we want to draw FCC, the atoms would be on the face, right? That face, the bottom face, the back face. So that plane 1, 1, 1 will cut through most atoms in FCC, right? Can you see that? That plane cuts through all the face atoms. So if imagine you have infinite unit cells around this unit cell, that plane will cut through all the most atoms inside of FCC crystal structure. And later on, I'm going to talk about plane densities. So on that plane 1, 1, 1, it has the highest plane density. It can give some very special mechanical properties. But here, just remember, 1, 1, 1 direction is important for FCC. And of course, for BCC, 110 direction is important. You can think about where's BBC? Oh, sorry. BCC, sorry. Okay. Can you imagine where's the plane 110? What does that 0 mean? 0 means there's no interception. So HLKK is 0. That means that plane has to be parallel to which axis? 110. Parallel to Z. So should be a plane cross through the cut through the face diagonal of the cube, the unit cell, but it's also parallel to Z. So that plane is important for BCC. Okay. Also mentioned, so that's how we find crystallographic plane indices. Now we talk about plane family, which is so same definition as the direction family. So if the planes are parallel to each other, they're equivalent, they belong to the same family, and we use curly bracket. With 3-digit numbers. Similarly, for example, 100 can include planes 100, 010, 001. And also we can have negatives. You can add all negatives overhead bar. Oops. If you want to. So they all belong to the same family, means they all have the equivalent directions. Okay. That's all we need to know about crystallographic point, direction, and family. Still, we have 4 minutes left. Well, you can use this time to look at your exam if you want to, or if you have class after this, feel free to go early. All right. Hope you guys have a good weekend. And remember, we have 2 homeworks due, and the one due today, I know some of you couldn't find all the informations. If you have glass or amorphous materials, you couldn't really find a crystal structure. That's fine. Just right there, there's no crystal structure for this material. And you have another homework due on Monday. Make sure you check out Moodle. It's already posted.